Hi, and welcome to a video on the law of exponential change. This is going to be about bacteria growth, and really, did you realize how important this law of exponential change was? It pops up everywhere. If you've seen a movie like Outbreak, this is kind of what's going on in this problem. It's uncontrolled growth of bacteria, except in this particular problem, hopefully we can control it. So here's the problem. Suppose that the cholera bacterium in a colony grows unchecked according to the law of exponential change. If the colony starts with one bacterium and doubles in number every half hour, what we want to do is write a model that could be used to calculate the number of bacteria after a particular number of hours. And then secondly, we want to figure out how many bacteria there will be after 24 hours. Now, you really don't need any calculus to do this. You can do this all with algebra. In fact, if we're looking at our time period, at time 0, we have, let's call B for bacteria, we have 1 bacteria. After a half hour, we have 2. After 1 hour, we have 4, 8, 16, 32, and so forth. So this would be 3 halves of an hour, 2 hours, 5 halves in an hour. And if you look at this, basically, this is 2 to a power, and the power here is the number of hours times 2, because the bacteria is growing or doubling every half hour. So our equation to represent this, or our answer to part A, could be y equals 2 to the 2 times t, where t is the number of hours. Alright, so actually we can do this problem pretty easily. I want to show you where this comes from based on the equation that we've been using a lot. So let's just verify that this equation is correct. And, well, you know it's correct, but let's verify that we can get it the other way too. So let's say we start out with y equals y naught times e to the kt, and you think there's no e in here. Where does that come from? Well, we're going to show you. You can use the information that we derived up here from the situation to get a few points, because what we need to do is figure out what our constant, or our k, is. So we need to find k, and in this case k is going to be greater than 0 because we have growth. So to do that, let's pick, we know our starting amount, or our y naught, was equal to 1. And then we could say, let's say after 1 hour. After 1 hour, if t equals 1, we have, right here you can see we have 4. So our y, our ending amount, is going to be equal to 4. If we plug all this in and solve for k, we should end up with an equation that looks a lot like what we got over here. So let's make sure that works out. Alright, so 4 is going to equal 1 times e to the k times 1. Nice, because all our numbers are 1. Alright, let's take the natural log of each side so we can get rid of that exponential. So natural log of 4 equals the natural log of e to the k, or you could say the natural log of 2 squared equals k times the natural log of e, which is just 1. And then we can take this 2 out in front, and we can say 2 natural log of 2 is equal to our k. Nice. So let's go ahead and plug that into our equation. Y equals y naught times e to the 2 times the natural log of 2 times t. Now remember, in the last video, if you watched it, anytime you have a natural log in the exponent and an e in the base, you want to kind of put those two together because they do cancel each other out. So let's go ahead and simplify. And using the properties of exponents, you can rewrite that exponent as the natural log of 2, e to the natural log of 2 to the 2t power, because you would essentially be multiplying those. And this turns out to be 2 to the 2t, y naught equals y. And if you look at what we have up here, this is going to match, because remember, our y naught equals 1. So this turns into y equals 1 times 2 to the 2t power, or 2 to the 2t power. Alright, so we've got our part A. Our part A, we've got y equals 2 to the 2t power. And after 24 hours, or our part B, when our time, t equals 24, because t represented the number of hours, we get y equals 2 to the 2 times 24, or 2 to the 48. And we are going to leave the answer like that. That is a lot of bacteria. if we try to write that out the long way, it's going to be a mess. So let's just leave it in exponential form. We've got our answer, we've got our model, and we can see how this method that we used probably in Algebra 1 or Algebra 2, making the table, figuring out what the formula was, how that goes along with our equation that models exponential growth and decay. All right, so I hope this was informative. I hope you enjoyed it. Keep watching.